Hi everyone, it's Mrs. Meehan, and in this screencast, I'm going to go over momentum, change in momentum, and impulse. So let's define momentum first. Now recall that Newton's first law tells us that objects remain in motion with a constant velocity unless acted upon by a force. So an object in motion will stay in motion, an object at rest will stay at rest, unless acted upon by a non-zero net force. That's what we saw in a previous unit. Now, in your experience growing up so far, you've most likely noticed that when you have two objects of different masses, so they are different masses, when they're traveling with the same velocity, the one with more mass is harder to stop. So the velocity is the same, but the masses are different. Now, when you have objects of equal masses, so now the masses are equal, but we have them traveling with different speeds, different velocities, each one's traveling at a different speed, the faster one is harder to stop. So when you have the two objects and their masses are different, but the speed is the same, it's harder to stop the larger mass. When the masses are equal, but one is traveling at a greater speed than the other, the faster one is harder to stop. So this brings us to a quantity called momentum, which is represented by a lowercase p. And that takes these observations into account. So momentum is equal to mass times velocity. So P equals mv. What that is showing you here in this equation is they're directly proportional to each other. If you increase the mass, you would increase the momentum. And if you increase the velocity, you increase the momentum. Now, something else to note. Now, we know that the momentum of a single object is the product of its mass and its velocity, P equals mv. But momentum, like force, acceleration, and velocity, is a vector quantity. So this is because velocity is a vector. When you have a vector quantity present on one side of the equation, it means the other side here, whatever it's equal to, in this case, is also a vector quantity. Mass is scalar, so it doesn't have a direction. And what this is just showing you is that if you increase the mass or decrease the mass, it's always going to be a positive number. You can't have a mass under zero. When you have a velocity, you can increase the magnitude, but you can also change direction of velocity, or say there's a negative velocity or positive velocity. Because of that, the direction of the velocity of the object, if velocity is negative, let's say, momentum will also be negative because mass can't make it negative. If velocity is negative, momentum is going to be negative. If velocity is positive, then the momentum will also be positive. So they are both quantities, and so whatever direction the velocity is in, the momentum will be also. Now, the unit for momentum is the product of the units in the formula. There's no specialized unit. For example, with power, we had the watt. With energy, we had the joule. But here we don't. So it's just the kilogram times meter per second. So kilograms comes from mass, and meters per second comes from velocity. So that is the unit right here of momentum, kilograms times meter per second. Let's try some practice problems before we move on to the next thing. So which has more momentum? A large truck moving at 30 meters per second, a small car moving at 30 meters per second, or they both have the same momentum? Okay, let's take a look. Now, in this case, both have the same speed, but the truck has the larger mass. So remember, our new equation here for momentum is P equals mv. If you increase the mass, you would increase the momentum. So since the mass of a truck is going to be larger than the mass of a car, the momentum will end up being larger than that of the car. Okay, next question. We have the momentum of a 20 kilogram object with a velocity of 5 meters per second. So for this, remember the equation is momentum equals mass times velocity. 20 times 5 gives you 100 kilograms times meter per second. What is the momentum of a 20 kilogram object with a velocity of negative 5 meters per second? So this is a negative direction. The magnitudes here are the same as the previous problem. However, velocity is negative. And since velocity is negative, then momentum will also be negative. The momentum will match the direction of the velocity. So for this one, it's negative 100 kilograms times meters per second. What is the velocity of a 5 kilogram object whose momentum is negative 15 kilograms times meters per second? So here we have to solve for velocity. So to rearrange the equation, we have P equals mv is the base equation. However, we are solving for velocity. So when you divide by mass on both sides, you end up with velocity equals momentum divided by mass. So negative 15 divided by 5 gives you negative 3 meters per second velocity. What is the mass of an object whose momentum is 35 kilograms times meters per second when its velocity is 7 meters per second? So again, you just have to rearrange the equation, remember. We are solving for mass this time. So divide by velocity on both sides. You end up with mass is equal to momentum divided by velocity. So 35 divided by 7 is equal to 5 kilograms. So we just talked about momentum, but next let's go over change in momentum. So suppose there is an event that changes an object's momentum. So you have an initial momentum, p sub 0 here, so just before the event, by a change in momentum, delta means change, remember, to a final, p sub f, the final momentum just after the event. The equation for momentum change would simply be the initial momentum plus the change in momentum equals final momentum. So something here with the change, something will change the momentum of an object. An example could be applying brakes to a car. So the momentum change equation is at the top here. Now remember, Newton's first law tells us that the velocity, and so the momentum of an object won't change unless the object is affected by an external force. So when an external force, F, acts on the object for a time, delta t, change in time, it delivers what is called an impulse. An impulse is represented by capital I. So this impulse to the object that changes its momentum. So impulse, an equation for impulse, is that force that's applied times the change in time. So we have an impulse. So impulse is equal to the final momentum minus an initial momentum. And it's also equal to a force times a change in time. Now, the standard unit for impulse, there's no specially named unit, just like with momentum, and you just use the product of the units of force and time. Now, the Newton second actually works out to be the same thing as kilogram times meters per second squared, and that is the same thing as momentum. So momentum and impulse have the same unit. Let's take a look at the effect of collision time on a force. So we know that the impulse, it's a force times the change in time, and that's equal to the change in momentum here. So change in momentum, it's that final minus initial. And this graph, what it's showing you is that if you change the duration or the time of an impulse by a small amount, you can greatly reduce the force on an object. So let's take a look here. You know, an object is moving and you start to apply force. Let's say you spend 10 seconds applying that force right there. The force over here is much lower compared to hardly any time spent applying the force. It is much higher up here, 250 newtons versus much smaller number here. You know, if you take half the time to apply a force, so let's say at 5 seconds, that's much lower still than if you apply hardly any time. So there is a dramatic decrease in force if you extend the time in which it is applied. So applying a force, let's say you're applying the brakes to a car as you're approaching a wall and you take 10 seconds to start slowing down, you know, the force is going to be much less. The force that is felt will be much less compared to waiting 5 seconds, might be a little bit rougher. But if you actually end up hitting the wall or hitting the brakes right before hitting the wall with such, you know, it would take a lot of force to stop the object. And so this is a, you know, great amount of force there and could cause some damage. Now, some real world applications in which the concept of impulse is applied. So trying to, you know, trying to increase the amount of time in which the force is applied. A lot of that happens in car design. For example, airbags help reduce the time it takes to stop an object from moving. In this case, it would be you, the person, because you'd be blocked by an airbag a bit as you continue to move forward after a car stops instead of just hitting the dashboard. Same thing with certain collisions and crush zones. That's taken into account in car design. Jumping and then landing. If you can increase the amount of time, you know, if you just land with straight legs, that's going to hurt a bit. But if you crumple a little bit as you hit the ground, you sort of let yourself, you know, bend your legs a bit as you land, that doesn't hurt as much. And you see it in a lot of other applications in sports, etc. Okay, so let's try a couple practice problems here. So we have an external force of 25 newtons acts on a system for 10 seconds. How big is the impulse delivered by the system? So here we have our force is 25 newtons, change in time is 10 seconds. Impulse is equal to force times the change in time. So 25 times 10 is 250, and you can say Newton seconds. You know, if it's easier to remember, it's that force is newtons, and then time is seconds. The Newton second is fine to use. Or remember that's also the same units as momentum, which is the kilogram times meter per second. You know, either units would be correct. In the previous problem, an external force of 25 newtons acted on a system for 10 seconds. We found that the impulse delivered was 250 newton seconds. What is the magnitude of the change in momentum of the system? So for this one, we know the impulse that was calculated in the previous problem was 250 newton seconds. Impulse is equal to change in momentum. So you can say that the change in momentum is 250 newton seconds. the momentum change of an object is equal to the B, impulse acting on it, which was just mentioned in the previous problem. Impulse is equal to the change in momentum, the final momentum minus the initial momentum. So the answer is B. Airbags are used in cars because they B, they increase the duration or time of impact in a collision. So by increasing the amount of time during the collision, the force required to reduce the passenger's momentum is reduced. This in turn can reduce or prevent injury since now you won't have as high of a force acting on you. One car crashes into a concrete barrier. Another car crashes into a collapsible barrier at the same speed. What is the difference between the two crashes? So for this one, our choices were, okay, is it the change in momentum would be the difference between the two crashes, the force on the car, the impact time, or both B and C are true. So the answer is D. Both B and C are true in this case. They're going to experience the same change in momentum. So they're hitting that wall there and they were traveling at the same speed. They had the same momentum and then they're both going to stop or their momentum will cease. That's going to be the same. However, the force on the car and the impact time, that's going to be a little bit different. So whether the wall is padded or not, the car experiences the same change in momentum and so the same impulse. The only difference is that the impact time has increased, which in turn reduces the force experienced by the car. An external force acts on an object for 0.002 seconds. During that time, the object's momentum increases by 400 kilogram meters per second. What was the magnitude of the force? So we're given time, we're given momentum. We know that impulse is equal to the force times the change in time, which is equal to change in momentum. So you can say that the force times change in time is equal to change in momentum. So you can just use that form of this equation here. So if the change in force, oops, sorry about that. If the force times the change in time is equal to change in momentum, then force, if we divide change in time from both sides, is equal to the change in momentum divided by change in time. So that would be 400 divided by 0.002, and that gives you 200,000 newtons. So letter C. Let's try this one out. So 50,000 Newton force acts for 0.03 seconds on a 2.5 kilogram object that was initially at rest. What is its final velocity? Now this one requires some multiple steps here. So we want to know the final velocity. So we know that the initial velocity is 0 since the object was initially at rest here, so 0. We know the force is 50,000 newtons, time is 0.03 seconds, and mass is 2.5 kilograms. Taking a look at some of the equations here, we know that impulse is equal to the force times change in time, which is equal to the change in momentum. Now, change in momentum could also be written as mass times the change in a velocity. So taking that, because if you're going to change the if you're going to change the momentum, you're going to change the velocity. So the force times change in time, as a result, you can take this equation and you can have it equal to mass times that change in velocity. Then you just rearrange it, so change in velocity, or you can also add in the fact that change in velocity equals your final velocity minus an initial velocity. So force times change in time is equal to the mass times the final velocity minus initial velocity. The next step, you could say that it equals mass times final velocity, since the initial velocity equals 0. So that just cancels out. That gives us an equation in which final velocity is equal to the force divided by the mass times the change in time. So when you enter that information into the equation, that gives you an answer of 600 meters per second for letter B. Additional practice problems that go with this lesson are the chapter problems numbers 1 to 28, and they can be found on Google Classroom.